Okay, let us start. So, we started off with Gelfand theory. So, that was looking at multiplicative linear functionals on a Banach algebra. Remember that the multiplicative linear functional simply means that it is a continuous linear functional plus it is multiplicative, that is product goes to the product. Now, this can be defined in any Banach algebra, it does not have to be commutative, does not have to have identity and so on. Okay. But for our course we generally restrict ourselves to a commutative Banach algebra. Sometimes it may not have identity, as we saw in the last lecture. The example was L1 of R with it has no identity. It is something which you can prove using the Fourier transform we have defined. In fact, if you know some Fourier analysis, this is a easy exercise. Okay. So, there are Banach algebras without identity and there are Banach algebras with identity, like continuous functions on the compact Hausdorff space. So, we continue studying these multiplicative linear functionals and we will see that they form a nice space. So, if I look at all continuous linear functionals on a Banach algebra, they sit in the dual space because they are all continuous linear functionals, and if they are multiplicative then they have certain property and they are a small subset of the unit sphere and which becomes a compact set. Okay. And we transfer these elements in the Banach algebra to functions on this compact space via what is known as the Gelfand transform. So, that is how you embed an abstract Banach algebra inside a concrete object like continuous functions on a compact Hausdorff space. Okay. So, that is the aim. Okay. So, let us continue. So, let us start with the following proposition. Suppose phi is in the spectrum of A. So, remember A is always a commutative Banach algebra with identity. Then and sigma A, remember, is the spectrum of A, which is the collection of all multiplicative linear functionals, right. Then some of the things are trivial, you have seen this in group homomorphisms and things like that, ring homomorphisms and so on, those will continue to hold, of course, right. So, A phi of identity equal to 1, of course, the identity has to be mapped to identity which is 1 on the other side. B, if x in A is invertible, then okay, maybe I use another letter here, then h of x is not 0 for every h in the spectrum of A, right. For every multiplicative linear functional, the value of that multiplicative linear functional at the point x is non-zero if x is invertible. Okay. C, okay, phi is already there. So, we can use phi modulus of phi of x is less than or equal to norm x, okay, for every x in A, okay, implies norm of phi is actually equal to 1, right, because phi of E equal to 1, right. So, it is less than or equal to 1 is the inequality in C and it is equal to 1 because identity goes to 1, right. So, the norm of any multiplicative linear functional is actually 1. Okay. Okay. So, let us prove this. Proof is straightforward and you have seen this in some form or the other. Okay. So, if x is a Banach algebra element is such that phi of x is non-zero. Okay. So, I am trying to prove phi E is equal to 1, right. Then well, phi of x equal to phi E times x equal to phi E into phi of x, right, but phi of x is not 0. So, this implies phi equal to 1, right. This is how you prove that identity goes to identity, right. So, that is a trivial assertion. B, if x is invertible, I want to say that no multiplicative, it is not in the kernel of any multiplicative linear function, right. Well, that is easy because we just proved that phi of identity is 1 and if x is invertible, this is x into x inverse and phi of x inverse, right. So, phi of x and phi of x inverse both of them cannot be 0, right. So, any invertible element will have to go to a non-zero value, right, via the multiplicative linear function, right, that is what we have seen. Okay. C, that is very easy. So, the last one is if mod lambda is greater than norm x, then you know that lambda e minus x is invertible, right. So, then lambda e minus x is invertible, okay. And if it is invertible from whatever we have just proved, no multiplicative linear. So, if mod lambda is greater than or equal to norm x, then lambda e minus x is invertible, and so it cannot be in the kernel of any multiplicative linear functional. That means, hence phi of lambda e minus x is non-zero. So, phi x is not equal to lambda for any phi, right, implies, well, if it is not equal to lambda for any lambda greater than or equal to norm x, that would imply mod phi of x is less than or equal to norm x, right. If it is, if the value is outside the ball of radius norm x, then it can't be outside the ball of radius norm x, right, that is what we have just proved. Okay. So, these are sort of straightforward results using the property that phi is multiplicative. Okay. So, from the above, now we are going to look at all multiplicative linear functionals as a space and see where it sits. Okay. So, from the above, sigma of A, so remember sigma of A is the spectrum of A, which is the collection of all multiplicative linear functionals. This is contained in A1 star. What is A1 star? So, that is the closed unit ball. Closed unit ball in A star, right. So, the 1 simply means that it is the unit ball. And so, we have the weak star topology on A star, and you can restrict that to sigma I, right. So, topologize. So, we are trying to make this space of continuously multiplicative linear functionals into a nice space with the topology and make it compact and so on. Okay. So, topologize sigma A with weak star topology, right, weak star topology on A star, right. So, we have a natural weak star topology on A star, you restrict that to your subset sigma A, okay, that is all is there. Okay. Now, if so, let us look at this space again sigma A. What kind of a space is that with respect to the weak star topology? Well, we claim that it is closed. Okay. So, claim, it is very easy, claim sigma A is closed with respect to weak star topology. So, when I write W star simply means that weak star topology. Well, what is weak star topology? So, let us quickly recall that. So, if I have linear functionals f sub alpha in A star, so net of linear functional f sub alpha converges to f in weak star topology if and only if f alpha at x converges to pointwise convergence, right, for every x in A, right, it is pointwise convergence. So, to show that sigma A is closed with respect to weak star topology, we know that it is closed if you have continuous linear functionals converging pointwise to something, that the limit is a continuous linear functional, right, from the uniform bounded responsive ladder. The only thing that is missing is the multiplicative property, but that is trivial, right. So, phi alpha converges to phi in weak star topology, then phi x y equal to limit phi alpha x y equal to limit phi alpha x limit phi alpha x, because phi alpha is multiplicative, I have phi alpha y, right, which is equal to phi x phi y, right. Pointwise convergence will preserve all these properties, right, that is a very straightforward assertion. And so, that it follows that sigma A is closed with respect to the weak star topology, but then you know that the unit ball, closed unit ball, is actually compact, right, with respect to the weak star topology by Banach-Kaloglu. Okay. So, by we know that A1 star is weak star compact, right, and sigma A is a closed subset of that. So, since sigma A is closed, sigma A is also compact, right, it is compact, and of course, it is T2 and T2. Okay. So, it is a Hausdorff compact, Hausdorffness is trivial. So, I will leave it to you. Okay. So, what we have done so far is starting with a commutative. So, before I write the next result and so on, let's look at whatever we have done so far. Commutative unital Banach algebra A, right, and we have sigma A, that is the collection of all multiplicative linear functionals on A, and this became compact and Hausdorff. So, it is a compact Hausdorff space. Okay. Now, our aim is to see if A, this Banach algebra, can be viewed as a concrete object sitting inside continuous functions on this compact Hausdorff space. Okay. Let us see. Okay. So, before we go to that, we have to study ideals and so on. So, this is something again you have seen in the case of maybe group theory or ring theory and so on. You look at kernels of homomorphisms, they have certain properties, right. If you have group homomorphism, kernels are normal subgroups. If you have ring homomorphism, kernels are going to be ideals, right, and that is precisely what we are going to do. Okay. So, let A be a unital Banach algebra. Okay. So, these are going to be easy definitions. So, I contained in A is a subalgebra if, well, it is a subspace and it is an algebra, right. So, if I is a subspace, so it is a subspace of A and is a subalgebra, and x y will be in I if x and y both are in I, right. So, I is closed under multiplication. So, that is what you mean by a subalgebra. Now, an ideal is a subalgebra which is closed under multiplication by things from A itself, right. So, I contained in I is said to be an ideal okay. So, here we will remember that we have commutativity, otherwise I have to define right ideal, left ideal and so on. Okay. So, since we are assuming commutativity, it does not matter. So, I is said to be an ideal if I is a subalgebra, and x y will be in I if x is in A. So, one of them could be in the whole space A, but the other one is in I, right. And right, so, what we are saying is A times I is contained in I, right, that is how it will be written. Okay. Okay. Now, so that is ideal. I is said to be a proper ideal, is said to be a proper ideal if I is not equal to the whole space, right. So, it is a proper ideal, and so it is easy to see clearly I is proper if and only if identity is not in I, right, because if identity is in I and I is an ideal, I can multiply with anything in A, I will get everything in I, right. So, I will be equal to A, so I will not be proper, correct. Okay. So, if it is not commutative, you have to define what is the left ideal, right ideal, and so on, and then continue essentially the same way. Okay. So, let us write down a proposition about ideals. What are important from our point of view are the maximal ideals. Okay. So, proposition, let A be a commutative, unital. So, I am assuming commutative, unital, and Banach algebra. Let I contained in A be a proper ideal. Be a proper ideal. Then several assumptions, all of them are quite easy to prove. Okay. So, A I contains no invertible element. B I closure. So, remember we have a norm and so on, and I is simply a subspace. Okay, we did not say it is a closed subspace. So, I can take the closure of that, right. So, this is closure of I. If I is an ideal, the closure is also an ideal, is a proper ideal. Okay, if I is a proper ideal, its closure is also a proper ideal. Okay. See, I is contained in a maximal ideal. Okay. Well, what is a maximal ideal? A maximal ideal is an ideal which is not contained in any other ideal other than the whole space, right. That is a easy definition. Any proper ideal is contained in a maximal ideal. Essentially, you can make I bigger and bigger, so that it becomes maximal. Okay. The maximal ideals are closed. Maximal ideals are closed. Okay. So, these are the assertions, and these are more or less straightforward from the definition, but it is something which we will be using, right. Okay. So, the first one is trivial. So, A is trivial. Why? Because if it I want to say it is a proper ideal. So, it contains no invertible element. If x is invertible in I can multiply anything in A, right. So, I can multiply it to x inverse, I will have identity in I, and so I cannot be proper. Okay. So, the first one is trivial. Second one is trivial because you want to say it is a proper ideal, right. So, B the okay. So, how do I say that the non-invertible elements in a Banach algebra. Remember, the invertible elements in a Banach algebra is open. So, non-invertible elements in a Banach algebra is closed and I is contained in that, right. So, I closure will also be contained in that. Okay, so, let me write down that. So, non-invertible elements in A is a closed set, is a closed sets, and I is contained in that, right. So, if I is proper ideal, then it has no invertible element. So, it is contained in the non-invertible elements, implies I closure, because it is contained in a closed set, its closure is also contained, right. So, this is contained in non-invertible elements. So, if it is contained in non-invertible elements, then the identity is not there. So, I closure is also proper, right. So, that is easy. C. I is contained in a maximal ideal. This is a routine application of the Zorn's lemma. So, I'll just give you one step, apply Zorn's lemma. Right. This is an argument which you would have seen at several places, like vector space has a basis and things like that, right. You apply Zorn's lemma. How do you apply Zorn's lemma? So, you look at consider, let us say, script f to be all u, where u is an ideal, right, proper ideal, containing I, right. So, you take something bigger than I, right. Then and look at all such proper ideals, right, containing I. So, you have a collection of sets actually, right. So, use the inclusion as a partial order, right, partial order. That means, A is less than or equal to B if A is contained in B, right. Both A and B are in F, right. And then to apply Zorn's lemma, you need to show that for any increasing chain there is a upper bound, right. So, if A1 is contained in A2, contained in A3, etc., and they are all in F, then union Aj is an upper bound. Well, what does that mean? Union Aj is a proper ideal. Well, it's an ideal is trivial and it is a proper ideal because none of them has identity, right. Each Aj is a proper ideal, okay. And so, it is an upper bound because it is in F, right. It is in script F, I will be contained in that, right. So, by Zorn's lemma there is a maximal element and that will give me a maximal ideal, okay. So, that is easy. So, complete the proof, okay. So, any proper ideal is contained in a maximal ideal, okay. So, D is clear because maximal ideals are closed. If it is not closed, you can take the closure, and remember these are proper ideals. So, closure is also a proper ideal, and but then it is supposed to be the maximal ideal. So, it should be equal to that ideal, right. So, maximal ideals are closed, okay. Now, so why are we interested in maximal ideals? Well, this will give us a correspondence between multiplicative linear functionals and maximal ideals. So, this is something you have seen in group theory, for example, homomorphisms, group homomorphisms and normal subgroups of that group, right. Because the normal subgroups appear as kernel of homomorphism, right. So, that is what we are going to do. Okay, so, let me write this proposition. At least we will start off the proof slightly. It is not a difficult proof, but there are certain things to be introduced. Okay. So, let A be commutative unital Banach algebra. Okay. The map phi going to kernel of phi. So, kernel of phi is all those elements in A that is mapped to 0, right. Phi is a linear functional. So, kernel of phi in the usual sense is a one to one map between sigma of A. So, remember sigma of A is the spectrum of A, which is the collection of all multiplicative linear functionals and the set of maximal ideals of A. Okay. So, well, there are more depending on the structure on A, there will be more things to say about this map. Right now, it is only an assertion that it is a 1-1 map from 1-1 map between sigma A and the set of maximal ideals, right, and the set of maximal ideals. Okay. So, if I start with a multiplicative linear functional, the kernel is a maximal ideal, and if I take a maximal ideal, there is a multiplicative linear functional whose kernel is there, right. So, as I said, this is something you would have seen in the case of group homomorphism. If I take the kernel of a group homomorphism, I get a normal subgroup, and if I take a normal subgroup, I can construct a group homomorphism whose kernel is precisely that normal subgroup. That is what we are doing with multiplicative linear functionals and maximal ideals. Okay. So, that is what one should. Okay. So, let us do the easy part. Proof, we will complete the proof in the next lecture, but let us do the easy part. So, let phi belong to sigma of A, that means phi is a continuous linear functional and a multiplicative homomorphism, right. Then kernel of phi is closed, right, because it is the 0 set of a continuous function. So, it is closed and it is an ideal, right. Why is it an ideal? Because if I take x in kernel of phi and y in script A, then phi of x y is equal to phi x times phi y, but this is 0, right, equal to 0. So, x y would be in kernel of phi, right. So, because of that, kernel of phi is an ideal, it is closed, and I want to say it is maximal. Why is it maximal? Well, it is maximal because if I look at, this is something you know from functional analysis, if I look at A quotiented with kernel of phi, this is one dimensional, right, and it is to C. Okay, because of that, it has to be maximal, right, because the quotient is a field. So, whatever you are quotienting with has to be a maximal ideal. Okay. So, what we need to show is well, it is also easy to see it is 1-1. So, kernel of phi is maximal and it is also 1-1, map phi going to kernel of phi is 1-1. Also, if kernel of phi 1 equal to kernel of phi 2. So, if I have, let us say phi 1 and phi 2 multiplicative linear functionals, and if phi 1 is kernel of phi 1 and kernel of phi 2 are same. So, from functional analysis you know that if I have two linear functionals whose kernels are same, they are multiples of each other, right. So, this implies that phi 1 equal to lambda phi 2 for some lambda in the complex plane and evaluate it at identity, right. So, evaluate at E to get lambda equal to 1, right, because left hand side you have 1, right hand side you have lambda equal to 1. So, if I take two linear functionals whose kernels are same, they are same, Okay. So, because of that phi going to kernel of phi is a 1-1 map. Okay. So, hence phi going to kernel of phi is 1-1. Okay. What we will show is that it is onto, that means given a maximal ideal. So, we need to construct given a maximal ideal, let us say M contained in A, we need to construct sigma in phi in sigma A such that kernel of phi equal to M. Okay. So, the construction is similar to what you have seen in case of group theory, but let us stop here. We will continue with the proof in the next lecture and complete it. Okay. So, we will stop here.